Hi everyone, welcome back. So today we're on lecture 19 and we're going to do an interesting topic, which is Fresnel reflection and transmission of plane waves. So we discussed plane waves in the last two lectures, and today we'll kind of continue in that direction and see how plane waves essentially reflect and I guess refract through a dielectric interface. And a lot of optical phenomena that you might have seen before, we can derive from first principles based on what we've developed so far in the class. So it's kind of interesting. Okay, so what kind of problem are we looking at? So we have some kind of a dielectric interface, which means that I have two media. So one medium is, let's say here, mu1, epsilon1, and then we have mu2, epsilon2, two different mediums. And I have an incident plane wave. It's coming in maybe like that. Should be a straight line at some angle. This is my surface normal. So we're coming in at an angle theta incident. So this is a plane wave. Say this is my incident k vector, A incident. And since my k vector is in incident this direction, my the electric field, since it's a plane wave, can lie anywhere in this plane, right? Which is like along this line or normal to the page. So we'll treat two different cases. So one case is when the E vector is normal to the surface of this page, right? In that case, the H vector should be along the surface so that E, H, and K form a right-handed coordinate system, right? So this is the case we'll treat first, and this case is called TE, transverse electric. Okay, TE to Z typically. So it stands for transverse electric. Should put this in capital. Transverse electric to Z. It's still a plane wave, it's still a TEM mode, a TEM wave with respect to its own coordinate system. But in this coordinate system, we'll say that this is the Z-axis, this is the X-axis. So it is transverse to Z, which means that if the Z-axis is going this way, since the electric field is coming out of or going into the page, it's perpendicular to Z. Right? So since the electric field is transverse to Z, it's called transverse electric. Okay, and of course, magnetic field is not transverse to Z because it has a component along this direction. Okay, the other case would be where this is the electric field and this is the magnetic field, right? Then in that case, the magnetic field would be transverse to Z and that is called TM to Z. Okay. So sometimes this is also called S polarization, more in the optics literature, or also called as perpendicular polarization. Let's see, there are alternative names to the same kind of case, which is the TE to Z case. Okay, so S basically means it kind of skips on the surface, right? So maybe that's like a mnemonic to remember it. And the TM to Z is called P polarization. So that becomes P. So P is when the electric field is in this direction or maybe in this direction. And the way to remember it is that P pokes the surface. So that's why it's P, whereas S skips on the surface, which means the electric field is kind of skipping like skipping rocks on the surface of water, right? So these are just mnemonics. So it would be, instead of perpendicular, it becomes parallel polarization. Okay, so given that we have this, what are we trying to do? We're trying to find how does this wave reflect and refract through this interface, right? So we have something that came in and part of it kind of goes in to the surface, into the second medium, right, at some angle. We don't know what this angle is yet. theta t, and part of it reflects back, right? So then I end up with a magnetic field in this direction, and then I have my electric field is still in the same direction because the direction of propagation now is this way. And the electric field has to stay the same. We'll see why, but it's essentially to satisfy. So I'll call this K1I because it's the incident, and this is K1R reflected because the electric field has to satisfy continuity, right? Okay, similarly, I have electric field out here. So this is the incident, this is the reflected, and this is transmitted. And then this is the magnetic field is in this direction. It's transmitted. And then I have my K2, which is in this direction. K2T in that direction. Okay, so given that we have these labels, I have one more label to make, which is theta R. Now we want to find what exactly happens to these fields, this angle, and this angle. Right? So we need to solve for that. Okay, so before we do that, we'll make some definitions. I'm going to call gamma TE as the ratio of the magnitude, the reflected electric field, over the incident electric field. That's the reflection coefficient, the TE wave, and tau TE is magnitude ET, transmitted electric field, over the incident electric field. Okay, so given these definitions, we can now write down the expressions for all these fields. So E incident is just some E naught, some arbitrary amplitude, times e to the ik1I dot r, that's the definition of plane wave, and it's along y hat. Okay, so we've seen that this is along y hat, right? Similarly, I can write down E reflected would be gamma TE now, because we've defined gamma now. E naught, that's the ratio of the magnitudes, e to the ik1r dot r, y hat. And then you have E transmitted is tau TE, E naught, e to the I k2t dot r y hat. Okay, so we still need to write these guys as well. So let's do that. k1I dot r is nothing but k1xx minus k1zz. So if you look at k1, it is in the positive x direction, there's a component, and the negative z direction, there's a component. Right? And those components, if I write as these, then you have to put the negative sign outside. Again, I can write this in terms of cosine and sine as well, which is k1x sine theta I minus k1z cosine theta I. Right? Because if you go back here, this is theta I, then this angle is also theta I, which means this component of ki, k1i is nothing but k1 cosine theta I. It's a k1 cosine theta I, and the x component becomes k1 sine theta I. So in a similar manner, we can write it for the reflected k, be k1x x plus k1z z, which is nothing but k1x sine theta r plus k1z cosine theta r. And similarly, k1t dot r is k2x minus k2zz. I should put actually a t here, r here, and an I here, because they are slightly different, they're not the same thing. So this would be k2x sine theta t minus k2z cosine theta t. Should rewrite this a little bit nicer. Okay, so we have these expressions for E and K. The only thing we need to write down now is the expression for H field. So the incident H is E naught over eta 1. The eta 1 is the impedance of the medium. A1 I dot R cosine theta I x hat plus sine theta I z hat. So if you go back here to the same picture again, since this is theta I, this is also theta I, so the x component will be cosine theta and the z component is sine theta. That's what we have here. And then we also have HR, which is gamma TE E naught over eta 1 e to the I k1R dot R minus cosine theta R x hat plus sine theta R z hat. And HT is tau TE E naught over eta 2 e to the I k2t dot R times cosine theta t x hat plus sine theta t z hat. Okay, so since we've now written down all of the fields, now what we need to do is to find what these values are for gamma, tau, in terms of the medium. Since, of course, we go back here, the only thing we are really given is this, and the incident field. Everything else we need to find. Of course, we're also given this. So we need to find this in terms of all of these quantities. Similarly, these guys in terms of these quantities, these guys, and these guys. Right? So all of this stuff on the right-hand side needs to be found in terms of these quantities which have been defined. And that's what we're going to try and do. And to do that, we start by simply applying the boundary conditions, since we know that boundary conditions need to be satisfied. So the next step is to apply the boundary conditions, which is that the tangential E must be continuous at z equal to 0. So if you go back here again to this picture, at this interface, when z is equal to 0, and the tangential component of E, which is of course this component, must be 0. Now in the top surface, you have two electric fields. You have this one and you also have this one, right? So this plus this tangential component should be equal to this. That's what we're going to write down. So from the field expressions that we wrote, we essentially get E naught e to the I k1 sine theta I. You have minus z cosine theta I, but z is 0. So we don't get that. Plus gamma te E naught e to the I k1 x sine theta r. Again, you have a plus z term, which goes to 0, is equal to tau te E naught e to the I k2 x sine theta t, and the z term is 0 again. Okay, so this has to be true for all x. For all points along that interface, this has to be true. So of course, it must be true also at x equal to 0, which we can set. And if you set x equal to 0, that gives you 1 plus gamma te is equal to tau te. Okay. This is a simple relationship, which is saying that 1 plus the reflection coefficient is equal to the transmission coefficient. And you get something very similar in transmission lines, because you can think of a transmission line as nothing but just a plane wave at normal incidence, right? So that this, what we're doing here is kind of slightly more complicated version of that. Okay, so now for this to be true, we know this is true always. Since this is true always, and we need this equation to be true as well, the only way that can be true for all values of x is if these terms cancel out. These exponential terms cancel out. So for the exponential terms to cancel out, we need this to be equal to this, to be equal to this. Okay? So essentially, we end up with k1 sine theta I is equal to K1 sine theta R is equal to K2 sine theta T. Only under this condition does this condition and this condition together basically guarantee that this equation is always satisfied for all values of x. Okay? Okay, so this condition is actually very important, and it is called, it's so important that I can't afford to have a bad box. So let's make the box again. Okay, so this condition is called phase matching. And we'll see why it's called that in a second. It's called the phase matching condition. Okay? Okay, so of course, we'll get to what it means. But from this, you can quickly see that this term and this term cancel, and you get theta I equal to theta R. Okay? And you also get this equal to this. So if I define, so let's say I have my K1 or K. K is the free space wave number, which is nothing but omega over the velocity of the wave in the medium. I can write that as omega over c times some quantity n. Okay? And this n is called the refractive index. Okay, and you can kind of see that. So refractive index is often defined as the ratio of velocities, right? So I can write k as omega square root of mu epsilon, right? So this is assuming, okay, that mu is mu naught. Then you have omega square root of mu naught epsilon naught times square root of epsilon r, right? So if I define n as the ratio of the speed of light in free space over the speed of light in the medium, speed of light in free space is mu naught epsilon naught. In the medium, it's mu naught epsilon r, right? Oh, sorry, it's inverse of this. Inverse, inverse, inverse. So that just becomes square root of epsilon r. And that's why k is nothing but omega over c n. Okay, they're all kind of representing the same thing. So if I write it in terms of refractive index, which is slightly more popular, I guess, in the literature, then you essentially get, this part gives you theta I equal to theta r, and this part gives you, so we have theta I equal to theta r, which is one relationship. And you also have n1 sine theta I equal to n2 sine theta t. Okay, so the combination of these two are called Snell's law. So hopefully maybe you've seen that. Snell's laws of reflection and transmission. So in a first course on optics, you would learn something like this. And now we see that it comes from nothing more than the boundary conditions. And the boundary conditions essentially gave us this phase matching condition. So we need to kind of interpret this phase matching. What does this really mean? Right? So let's see what it is. So if I redraw my figure, right, and I just draw the k vectors. So I have an input k or an input plane wave. I'm just kind of exaggerating it a little bit. And then you have your output plane wave or reflected plane wave. You have this transmitted plane wave. Okay, so each plane wave has a wavefront associated with it. So this I'll say is coming in, this is going out, this is coming that way. So each one has a wavefront associated with it, right? So it's perpendicular to the direction of propagation. So I'm drawing let's say, the peaks of this wavefront. Incident wavefront looks something like this. Okay. I'll also extend this one. That. So extend maybe this one. Okay. So we know that the speed of light in this medium, let's say it's, free space, epsilon naught, and this one is some other medium, epsilon 1, where epsilon 1 is greater than epsilon naught. And we know that the speed of light would slow down in this medium because the epsilon or the refractive index is larger than the refractive index in free space in this medium, right? So which means if it slows down, then we know K is omega over C, or omega over V, I should say. K is omega over V, which means K becomes large. If K becomes large, so this is 2 pi by lambda, right? Or you could say V equal to F lambda. Right? So if V goes down, then lambda also must go down because frequency remains the same. Or another way to say that is that K goes up, then lambda must go down because K is 2 pi by lambda. Right? Which means the wavefronts in this other medium must be closer to each other, right? Something like that, because it slowed down in this medium, the wave. But if it becomes suddenly slower in the other medium, then the peaks don't line up anymore, right? And that doesn't make sense because the phase at this boundary must be the same on both sides, right? The phase here and the phase here must be the same because you have a maximum here, you cannot have a zero here because there has to be that continuity in phase. So the only way the peaks can line up with a smaller wavelength is if this wave bends like that. Now you see that this wavelength is smaller, but the peaks are all lined up. And the only way that could happen is if this wave got bent, right? That's the intuitive kind of explanation. So I'll draw it out just to kind of clarify that. See, now you see that the wavefronts are closer to each other, which means the wavelength is smaller, but still all the peaks are lined up, right? Now for the reflected wave, that doesn't have to be the case. So the reflected wave wavefronts would be lined up something like this. And then of course, continuing on to this part. It's not gonna let me draw it, but you get the idea, right? That's the reflected wave. Okay, reflected wave has the same wavelength, it's just flipped, but everything is satisfying this phase matching condition at this boundary. And the reason it's called phase matching condition is because, again, the phase has to be matched on both sides. Now, mathematically, why does it turn out to be like that? So if I kind of go back and clean up this image a little bit, just to make it a little easier to understand. Right, I had a k vector, which was this one coming in, and that had some length. To match the phase, you only need to match the wavelengths along this direction. Right? This is the actual wavelength of the wave, but I only need to match the wavelengths in this direction, in the x direction. Right? Which is the same thing as saying I need to match the k vectors in this direction. So I have some k, but I only need to match k times cosine of this angle. Similarly, I have some k here. If I match the k along this direction, cosine of this angle, then they get matched up. But we define the angle with respect to this theta I. So which means it's k times sine theta I. And that's why you have k1 sine theta I equal to k1 sine theta R equal to k2 sine theta T. Okay, so enforcing that condition is exactly the same as enforcing the fact that the phase has to be continuous at this boundary, which essentially comes from the fact that the electric field has to be continuous, right? So that's what the phase matching condition is. The only case where the phase matching condition does not need to be satisfied is if you have a current, magnetic current distribution on this interface. Okay, then you know that the electric field Doesn't have to be continuous if it's a magnetic current distribution. And then in that case, you don't have to satisfy phase matching. Okay? But that has to be a surface current distribution, not a volumetric current. Anyway, so that's the kind of intuitive explanation for this phase matching condition and why that also leads to Snell's law of reflection and transmission. Essentially, why the wave has to bend for it to satisfy the continuity of phase. Okay. So this phase matching is a very fundamental thing because it essentially represents continuity of the electric field. And we'll use it again and again when we do waveguides in the future as well. Okay, so now to get the values of gamma and tau, we need to apply boundary conditions for the magnetic field. So if you apply boundary conditions for the magnetic field, you can show easily that you end up with this equation for eta 1. Same thing, you apply it at z equal to 0. And you try to show that it has to be true for all values of x. And you end up with this relationship, sine theta t over eta 2. Okay, so we can go back to the magnetic field and take a look. And we only have to satisfy the z, continuity of the z. But we already have what these values satisfy, right? So essentially equate these things, and that gives you the relationship that we had down there. Not along z, sorry, along x, my bad. So the z was in this direction and x is in this direction. So essentially it is equating this term plus this term equal to this term. And once again, the exponential factors can be gotten rid of, and then you're left with what we wrote down there. Okay? Okay. So this can be simplified a little bit because we know what Snell's law gives us is that theta I equal to theta R. So I can take it to be common, and that equal to cosine theta t over eta 2. And I know tau is nothing but 1 plus gamma. So write it out like that. And now I have a relationship from which I can solve for gamma, which is fairly easy to do. You can show that gamma turns out to be eta 2 cosine theta I minus eta 1 cosine theta t over eta 2 cosine theta I plus eta 1 cosine theta t. Okay. So this is a very important relationship. And from this, we can also find tau, because 1 plus gamma is tau. Turns out to be 2 eta 2 cosine theta I divided by the same denominator plus eta 1 cosine theta t. Okay, so these are called the Fresnel transmission and reflection coefficients. Fresnel, this is the reflection coefficient, and this is the transmission coefficient. Okay. Okay, just recall that eta is nothing but square root of mu over epsilon. So in free space, not free space, in a dielectric medium where mu is equal to mu naught, this becomes nothing but mu naught over epsilon naught, epsilon 1 over square root of epsilon r, right? Which means that, or I can write it as square root of mu naught over epsilon naught times 1 over n, because the square root of epsilon r is n, right? So that's the relationship between eta and n. And of course, n is also related to k. Okay, so this is for TE. Now for TM polarization, which was the other case, we'll just do it very quickly. I'm not going to go into the details again. TM to Z. was you had the medium, and then you had the k vector coming in this way. Electric field is now pointed out like that, and then the magnetic field is coming out of the page. Okay, so in that case, gamma Tm turns out to be minus eta 1 cosine theta I plus eta 2 cosine theta t over eta 1 cosine theta I plus eta 2 cosine theta t. And similarly, tau Tm is 2 eta 2 cosine theta I divided by eta 1 cosine theta I plus eta 2 cosine theta t. That's the Fresnel transmission and reflection coefficients for the Tm polarization. Okay, so given these transmission and reflection coefficients, there are many interesting phenomena which we can discuss. So let's do that. The first one is Brewster angle. So you want to see at some angle, can I make the reflection coefficient equal to 0? So we'll start with the Tm case, right? And if I try to set this to 0, go back here. So the numerator, this numerator has to be equal to 0. Right, so what do I get when I do that? I get cosine theta I is equal to eta 2 over eta 1 cosine theta t, which is nothing but eta 2 over eta 1 square root of 1 minus sine square theta t, which is the same thing as 1 minus k1 square over k2 square sine square theta I, right, from Snell's law of transmission. And this is square root of 1 minus sine square theta I. So I can equate these two and get an expression for theta I. Okay, so I'll write down the final expression for theta I, which is the Brewster angle, is turned out to be sine inverse square root of epsilon 2 mu 1 epsilon 2 minus epsilon 1 mu 2. So now I've replaced etas and k's and everything with just epsilon and mu, right? So eta is square root of mu over epsilon, k is omega square root of mu over epsilon. Omega square root of mu epsilon. So if I put those terms in, I get this expression, mu 1 times epsilon 2 square minus epsilon 1 square. Again, in non-magnetic medium where mu 1 is equal to mu 2, so if mu 1 is equal to mu 2, and this becomes square root of epsilon 2 over epsilon 1 plus epsilon 2. So if I come in at this angle, at this specific angle, then I come in like this. There's no reflection, which means everything just goes through. Whatever came in, went through. Okay? This is for Tm polarization. Now, if I try to do the same thing for Te, gamma Te equal to 0, implies my Brewster angle, some incidence, becomes sine inverse square root of mu 2 epsilon 1 minus mu 1 epsilon 2 divided by epsilon 1 times mu 2 square minus mu 1 square. And if I make this medium non-magnetic, if mu 1 is equal to mu 2, then this becomes infinity. This is, of course, not realistic. Essentially, it's saying that theta Brewster does not exist for TE polarization. Okay, so one kind of way to remember this is that if I have Tm polarization, that means my electric field is, let's say, oscillating back and forth like this. So when it comes in and excites this other medium, I'm exciting dipoles in this direction. Because the dipoles are in this direction, their radiation has a null. All of them have a null in this direction, right? So that's why there is no radiation in this direction or no reflection. And whereas in TE case, the electric field is this way. So when it comes in, the dipoles are radiating as big circles in this cut or in this plane, because the null would be out of the page. And that's why you have some reflection back. So that's just an interesting kind of I would say, intuitive explanation for why TM polarization might give you a Brewster angle, but TE does not. But it doesn't completely explain the phenomena very accurately, because that should be true for every angle, but you only have it for one angle, right? So it's just an interesting or a useful, intuitive way to remember which polarization has Brewster angle. But of course, you don't have to remember it that way if you don't need to, right? So is this and put it in here equal to infinity when mu1 is equal to mu2. Okay, so if I actually plot the gamma as a function of theta incident, then for TE, just increases as you come to larger and larger angles. Whereas for TM, there is a dip down to 0, and then it increases like that. See if I can also get this to be a curved line. Like that. Okay, so this is for TE, and this is for TM. And this angle here is theta incident Brewster. Okay, so it's very useful, Brewster angle. It's used to make polarization filters. So for example, if I have a filter like that, and I come in with light that has both polarizations, TE and TM, right? TM would be going in completely. This is TM and TE, right? And what is reflected back would be TE. So this would be TM and TE, because TE has both reflection and transmission, whereas TM only has transmission. Right? So I can separate the polarizations in the reflected field. Right? So this creates a polarization filter, basically. So what I look at has only TE polarization now. So if, for example, if this was water, right? So if this was maybe water, it has some dielectric constant, and I am shooting a picture of this water and there's a fish in here somewhere, right? I know that if I'm shooting at this at a particular angle, then the only polarization that's coming into my lens is a TE polarization. So if I put a polarization filter here, filters out TE. So TE cannot enter my lens then, which means what? Which means the glare from this reflection is completely avoided. So the only image that you can get, in the image that you take of the water, of the lake, let's say, you don't have this big glare from the surface of the lake. So only light that's coming from inside the lake, which contains all polarizations maybe, enters the lens. So you can avoid this glare and you can see more clearly what is inside the water. So in photography, that's a trick that they use, which are the polarization filters, in order to make sure that, you can see inside the water without this glare from the surface. Okay. It doesn't even have to be water, it can be even a glass. So let's say you want to take a picture of something inside behind glass, behind a window or behind a glass. Then if you shoot at the right angle, you can avoid this glare from the glass itself, with a polarization filter. And there are also other applications of Brewster angle which are interesting. But in the lab, it's typically used to make these kind of polarization separators or polarization filters. Okay, so the next interesting phenomena we should look at is total internal reflection. So we kind of introduced this earlier when we did evanescent waves. We said that if I take a prism and I come in at a certain angle, all of the light is reflected back and it excites this evanescent wave behind the prism. So that was a couple of last lecture or 2 lectures ago. And we call this the Kretschmann configuration, to detect molecules and things like that, right? So we said there's an evanescent wave out here. And all of the power is reflected back. And we also calculated that all the power would be reflected back. Yeah. Because the evanescent wave doesn't take any power from the incident light. Right? So we want to actually establish this phenomenon is called total internal reflection, and we want to establish that. Okay. Okay, so for simplicity, we'll assume mu1 equal to mu2. Assume this. And we also assume n1, the refractive index of medium 1, is greater than medium 2. So of course, this is without loss of generality. If it's the other way around, then you have to come in, the incident light has to come in. Essentially, the incident light has to come in from a denser medium to a rarer medium to observe total internal reflection. In that case, the transmitted angle can be given by sine inverse from Snell's law, n1 over n2 sine theta I. Again, I want this to be equal to 90 degrees. So what does that mean? So I'm coming in at some angle, at coming in at some angle, and I want my reflected or refracted ray to go along the surface. Okay, that's what that means. When that happens, so the angle at which that happens is called the critical angle. Okay, so theta I, which is now it becomes critical, which I'll call as theta C, is sine inverse n2 over n1. Of course, right? Because if I take this sine onto this side, this becomes 1. And then I take n2 over n1 to this side, and I take sine inverse on both sides. Okay, so this is called the critical angle. Beyond the critical angle, if I come in, so if I come in at an angle beyond that, then all of the light is reflected back. Okay, and that's called total internal reflection. Okay. Okay. So we want to see what happens to the transmitted field ET beyond theta C. Okay. So we know cosine theta t is equal to square root of 1 minus sine square theta t. Right? That is equal to square root of 1 minus sine square theta I over sine square theta c. Right? Because sine theta c is n2 over n1. And if I replace sine theta t with n1 sine theta I over n2, take the square, I can replace n1 square over n2 square with 1 over sine square theta c. That's from this one. Okay. Now, since theta I is greater than theta c, since we're coming at an angle greater than the critical angle, implies that cosine theta t is now imaginary. Right? Because this term is greater than 1. So square root of 1 minus something greater than 1 is square root of something negative. So you pull the negative sign out, and that gives you an I. And then you essentially get cosine theta t to be imaginary. And we can essentially say cosine theta t will write as some I alpha, which is I square root of sine square theta I over sine square theta c minus 1. That's what alpha is. So alpha here is nothing but square root of sine square theta I over sine square theta c minus 1. Right? And sine square theta c is n2 square over n1 square. So I can essentially write this as n1 over n2. So I pull the sine square theta c out. That becomes square root of n sine square theta I minus, I should also write another sine square theta c here because I pulled it out from the denominator. But instead of that, I can write n2 square over n1 square. Again, I can convert this to etas, which will be more useful to us. And since I know n1 over n2 is eta 2 over eta 1, This is what I get. It's eta 1 square over eta 2 square. Okay. All right. So now that I know what alpha is and I know that cosine theta t is imaginary, if I go back and look at my electric field, which was gamma TE, or in this case, we're doing TM, let's say TM, E naught, e to the I kt dot r, that was gamma Tm, E naught, e to the I kt, x sine theta t, plus z cosine theta t. Now I substitute cosine theta t to be I alpha. That gives me gamma Tm, E naught, E naught, e to the I ktx sine theta t times e to the minus alpha ktz. And this is exactly what we wanted to show, which is that along z, you get an evanescent wave. Okay. So essentially, I'm saying that if I come in at an angle larger than the critical angle, then along z, you have an evanescent wave. And we saw that using the thought experiment last time, which is a frustrated total internal reflection. But now we've established it more formally. Okay. We also want to look at what happens to gamma Tm. We want to show that gamma Tm is 1 in magnitude, right? Because only when gamma Tm is equal to 1, you can prove that you have full reflection. Okay, so if I go back and write this as cosine theta t, eta 1 cosine theta I, divided by eta 2 cosine theta t, plus eta 1 cosine theta I. And I can replace cosine theta t with I alpha now. So I end up with I alpha eta 2 minus eta 1 cosine theta I over I alpha eta 2 plus eta 1 cosine theta I. I'll make a quick substitution. So I'll call this term A, this term B. Then I end up with IA minus B over IA plus B. This is nothing but minus B minus IA over B plus IA. Okay, and this I can write as an exponential function because, let's just say that I say if I said B plus IA equal to some R e to the I theta, so I write it in polar form, then B minus IA would be R e to the minus I theta. So when I take the ratio, R's cancel out, and that gives me B minus IA over B plus IA is equal to e to the minus 2I theta, right? Where theta is tan inverse A over B. And based on the polar definition, I'm going to erase all this. Hopefully, that's not too difficult to remember. And we can write it out as nothing but minus e to the minus I 2 tan inverse A over B. Okay. This I can rewrite as e to the I pi minus from properties of the tan inverse of A over B. And this is purely pure complex number with magnitude equal to 1, right? So essentially we've established that the magnitude of Tm, gamma Tm, is equal to 1. So this is proving that it is in fact proper total internal reflection or total reflection. But we're also interested in this phase term. So what this is saying is that when I have a wave that came in and got reflected, it didn't just get fully reflected. Obviously, the magnitude is the same in the reflection, but there's an additional phase factor that got added, which is given by this. So we need to investigate that a little bit more. So this phase factor, phi Tm, I'll call it, which is a function of theta I, is pi minus 2 tan inverse A over B. Okay, and I can, this is essentially the same thing as 2 times tan inverse B over A. Okay, when B over A is greater than 1, greater than 0. And that's the case. If you go back and look at B and A, essentially alpha times eta is always greater than 0. Positive eta 1 cosine theta I is also positive. So you can write it like that. And now I can substitute the values of B and A in there, and that gives me PTM as a function of theta I is 2 times tan inverse eta 1 cosine theta I over alpha eta 2. Okay, I can substitute the value of alpha as well in here, and that gives me PTM theta I equal to 2 times tan inverse eta 1 square cosine theta I over eta 2 square root of sine square theta I minus eta 1 square over eta 2 square. Okay, this phase shift is called the Goos-Hanchen phase shift. So it's a small amount of phase shift that occurs when you have total internal reflection. Okay, you can also derive this same thing for TE. So I'm not going to go through the derivation again, but I'll write the final expression. 2 tan inverse of eta 2 cosine theta I over eta 1 square root of sine square theta I minus n1 square or eta 1 square over eta 2 square. That's for the TE case. Okay. So this Goos-Hanchen phase shift can be interpreted in different ways. So intuitively, what's going on? That you have an incident wave that's coming in. Coming in like that. On this side, you have an evanescent field that's decaying like that. And then there's a reflection from here. So one way to interpret the phase shift is that this evanescent field that's out here, right? This is some kind of, you can think of it as some kind of stored energy, right? So if depending on the TE or TM case, it can be the capacitive or inductive kind of stored energy. It's like a small capacitor in space or a small inductor in space. So when you have a reflection and there's a capacitor that's loading this incident plane wave, it introduces a phase shift. Right? That's what, from the point of view of circuits, is how do you make a phase shifter? You add some capacitance or inductance that you can tune, and then that adds some phase shift. Right? So the same way, the evanescent field that is there is adding a small amount of phase shift. Okay, because it's some kind of a parasitic loading you can think of, or some kind of passive loading. Another way to interpret it is to say that, okay, you have a field that came in, plane wave that came in, and it did not reflect just from the surface. It actually went into the medium a bit because there is an evanescent field in the medium and then got reflected. And because it went in and came out, it looks like there is a transverse phase shift. So if you actually think of this as a plane wave, adding a small phase shift to the plane wave is like saying you shifted the plane wave to the right. If you look at the wave fronts, that's the case. That's another kind of way to interpret this Goos-Hanchen phase shift because of the evanescent field. But essentially, whenever you have an evanescent field on the other side, you have this kind of behavior. So even in PEC, if I have a PEC on this side, and I have full reflection, so a metal, and that would happen at any angle, even in PEC, there is an evanescent wave inside the medium, okay, which means that there is this kind of small phase shift that occurs. Okay, and this has an implication because this phase shift is angle dependent. So if you come in at a different angle, the phase shift is different, which means that different rays that are reflected from different angles. If I have a source here that's putting out many rays along different angles, and let's say they all are undergoing total internal reflection, each of them reflects with a slightly different phase. Because each of them reflects with a slightly different phase, it's like you're adding some kind of phase gradient on top of your reflected wave. So the beam actually squints a little bit. Okay, so it leads to beam squint, a small amount of beam squint. Because all of these rays that are going at different angles are all slightly phase shifted. So instead of this beam reflecting off exactly, the beam has a slight phase shift or a slight tilt. Okay. It's also very useful for biosensing again, because the phase shift that is modulated onto this reflected ray is very sensitive to this eta 2 and eta 1, right? So essentially, if I place some kind of material here, or like we looked at the Kretschmann configuration the last time, in Kretschmann, the nice thing is that you essentially only have to measure the amplitude, right? But if you're capable of measuring the phase, which in optics is harder, but in microwave, not that hard, if you can measure the phase and if you can kind of detect these very small phase shifts, then you can detect the presence of a different molecule here, because the dielectric constant of this region would be slightly different. And another implication is in optical waveguides, which we'll see in the next lecture, that I can have TE propagation and TM propagation using total internal reflection. And because TE and TM have slightly different phase shifts from this Goos-Hanchen component, when I go through many, many reflections over a long waveguide, the TE and TM polarizations have a total phase shift because of each Goos-Hanchen component that's slightly different. So you end up with birefringence as well. So we looked at birefringence earlier. So essentially you come in, you have TE, TM polarizations, they're in phase in the beginning, but after propagating through this medium or through this dielectric waveguide, they would have a slight phase shift, and then you go from linear to circular polarization, right? That could happen in a dielectric waveguide. Okay, so these are the different implications of this small Goos-Hanchen phase shift. So it's something to keep in mind and to know. Okay, so the next thing we'll look at, which is the last topic for today, is what if I have three dielectrics? Okay, and this kind of an interface is interesting. Right, so what does it look like? So we'll go through this kind of roughly, but not necessarily roughly, but since we developed two dielectrics, it'll be a little bit easier to develop it. So I have some incident field coming in here, and I can label these as epsilon1, epsilon2, epsilon3. Okay, let's use blue. So they come in at some angle. So some of this goes into the medium and then comes out the other end, and some of it is reflected at this surface. Again, at this surface, there was some reflection. Some of it went out, and some of it got reflected back. Then again, at this interface, you have transmission and reflection. Again, transmission, reflection, and so on. You'll have infinity of these. Keeps happening over and over again. And we want to study this kind of phenomena. So you want to label this a little bit. So I label the reflection and transmission coefficients as R and T. Of course, they're different for TE and TM case, but we'll just treat the general case. So if I have reflection at this interface when I'm going from 1 to 2, I'll call it R12. Transmission from 1 to 2 is this one. And then when I'm coming back this way, so I'm coming from medium 2 to 1, and then there's a reflection that I'll call as R21, and similarly transmission would be T21. So that would be transmission that's coming in like this and going this way. That's the transmission coefficient. At the other interface, we only have one reflection coefficient and one transmission coefficient because we don't have waves coming in from outside. Since we have nothing coming in this way, we only have these ones. Okay, based on these definitions, I'll also label these fields. So I'll call this as E incident. I'll call this as E0 reflected, the first reflected wave. This is E1R, E2R, and so on. And this I'll call as E1T, E2T, and so on. Okay? I can put some arrows to avoid confusion. These are all going out this way. These are all going out this way. Okay? Okay. So can write down equations now. E1 transmitted is nothing but E1 incident. So a wave comes in, it's the incident wave. So if I propagate through this medium through some distance, it picks up some phase, and then it comes out from this direction. Right? So incident comes in, I have a transmission coefficient to go into medium 2, phase from the propagation, which I'll call e to the I phi, and then coming out from the second interface. Okay, now this is the important part, is that this phi is K2 cosine theta t, theta 2, times d. Okay, where this is theta 2. So why is that? Right? Why do I have to put the cosine theta t in there? So if I have a wave propagating in this direction, that corresponds to a plane wave, which is everywhere in space, going in that direction. Right? If I want to know how much phase this picked up from this plane wave front to this wave front, then I have to look at the k component in this direction. Right? Because this plane wave can be decomposed into, and this plane wave can be decomposed into one going that way and one going this way. The one plane wave going this way, it doesn't have any phase difference in this direction. At this point, this wavefront and this wavefront have the same phase. Whereas the plane wave going in this direction is like this, so it accumulates phase in this direction. Right? And that's why you need to look you're not really looking from this point to this point, from this point to this point, you're looking actually from this wavefront to this wavefront, because this ray represents a complete plane wave. Okay, so it's kind of important to understand why that's the case. Okay, so once you understand that, essentially we can write out all the other equations fairly easily. E2t, BE1, E in, T12, e to the I phi, which is this part, and then it went till here, and then you have a reflection here, right? 2, 3, then you have another phase shift, another reflection, another phase shift, and a transmission. Okay, so the reflection R2, 3, backward propagation, same phase, you get the same phase, one more reflection, forward propagation, and transmission. Okay, so if I write it for the mth case, the mth transmission, that's fairly easy. You have your incident wave, the first transmission, the last transmission, right? And then the first phase propagation times a single bounce path, which is one reflection on the right, one reflection on the left, one reflection on the right, or I should say maybe one reflection on the right and then one reflection on the left, reflection on the right, reflection on the left, two-way phase propagation to the m. And you can clearly see that when m is equal to 0, you end up with this. When m is equal to 1, you end up with this. And when m is equal to 2, you end up with this. So maybe I should say this should be m minus 1. M plus 1. So when m is 0, you get this case. Okay, so now what we want to do is we want to add all of these up because we want to see what is the total field after all of these infinite reflections going out this way. And so you should keep in mind that this ray corresponds to a wavefront everywhere in space. This also has a wavefront. This also has a wavefront and so on. So really all of these wavefronts are everywhere. So you want to know what is the total wavefront that's coming out, right? It doesn't mean that there's only ray here and they don't interact. I mean, they don't interact, but they add up in space because they both represent a plane wave that's everywhere. So what is that? So that corresponds to the total summation over all of these terms. E total, which is summation over m, EMT, where m goes from 0 to infinity. So that is E in total, E12, E23, e to the I phi, summation m equal to 0 to infinity, R12, R23, e to the 2 I phi to the power n. So that's a geometric series. Summation x when x is less than 1 is 1 over 1 minus x. So that's pretty simple. So this just becomes E in T12, T23, e to the I phi over 1 minus R21, R23, e to the 2 I phi. And I wrote it like this because then I can just rewrite this as the total transmission, T, which is E transmission over E incident, is equal to this. Okay? Okay. We can do the same thing for the reflected waves. Do it a little bit more quickly. First reflection is nothing but R12 E in, pretty trivial. The reflection after one bounce is T12, R23, T21, two-way propagation, E in. And you can write the same thing for the general case, which would just be T12. So one transmission at the beginning, one transmission at the end. First reflection, e to the 2 I phi, E incident, times the bounce path. R21, R23, same bounce path, 2 I phi, the power n. Okay, so I can write this out also as a series, do the summation and everything, the geometric series. That gives me a final result of R12 plus T12, T21, R23, e to the 2 I phi over 1 minus R21, R23, e to the 2 I phi whole thing times E incident. Okay, so again, I can kind of take the E incident onto the inside and then make this the total reflection coefficient. Okay. Okay, so essentially it comes out to be a nice term. You don't have to worry about all these infinities because they disappear from the geometric series. And now we can reduce this a little bit more. So if I say let medium 3 equal to medium 1, so it's just a dielectric slab inside some background medium. So note further that T12, T21 would be equal to 1 minus R12 square. And of course, you know, R21 is nothing but minus R12, right? Because eta 2 and eta 1 get switched when you write down the reflection coefficients. So if you do all of this, then you end up with the reflection coefficient R simplifies to R12, 1 minus E to the 2 I phi divided by 1 minus R12 square e to the 2 I phi. Okay, so this is very interesting, right? if you go back to this picture and look at our dielectric interface, you have all of these reflections, and you have all of these transmissions. It's a very complicated picture. But under a certain condition, you can make all of these reflections equal to zero, the sum of all of them rather. You can make the sum of all of these reflections equal to zero. What is that condition? That condition is when 2I phi, when 2I phi is equal to 2m pi, right? That becomes 1, this becomes 1, and this whole thing becomes 0. So no reflection, right? And that's really amazing. So this essentially reduces to the condition that k2d cosine theta t is equal to m pi. Okay, so this is called a resonance condition. This resonator is called a Fabry-Perot resonator. So if you go back here, we did this for two dielectric interfaces, but it doesn't have to be. This can be a mirror, and this can be a mirror with some level of reflection and transmission. This has some reflection and transmission, and this can all be free space or some medium. As long as you have reflection and transmission at this boundary and this boundary, and you're coming in at some angle, all of this mathematics is the same, right? So that's how you make a Fabry-Perot cavity. You have a mirror here, you have a mirror here, and they have very high reflectivities. So 99%, 99%, 99.999%, which means that when I come in here, most of the power is reflected back. Only very little made it in. But still, you can have zero reflection coming out, the total reflection. So although most of the power is reflected out here, it may look like how can these little ones that come out here cancel this? In fact, they can, because even when you come in here, most of the power is reflected in. So that 1% that made it through came in here, and over time that builds up, right? Because in steady state, we are saying that it cancels what was reflected in the beginning. But if you look at the transients, it came in, most of it reflected back, but kept putting power into this medium and kept building up, builds up, and at resonance or once you reach steady state, all of that buildup of power in here, which would be very large, energy inside this medium would be very large. All of that would essentially contribute quite a bit of power leaking out. That would completely cancel this, and then in steady state, you get a complete transmission, no reflection. So if you look at, if you're standing out here and you look at this with an eye, maybe this way, what would you see? You have an instant wave that came in, power reflected was very strong, and then slowly that reflected power starts to drop, and then eventually goes to zero. Transmitted power slowly starts to rise and eventually goes to 1. And basically that's when the steady state is reached. And then you have full transmission. And but that only happens at certain frequencies. And those frequencies are given by this relationship. So that's called the resonance condition. So what we've essentially developed is nothing but a filter, right? Because only at certain frequencies this is happening. And this is the time domain model for a filter. And so if you plot this, say as a function of frequency, I'm plotting the transmission. Right? Your Fabry-Perot transmission will look like this. So at certain frequencies, you will have these resonances. And this separation is called the free spectral range. FSR. And FSR is been calculated pretty easily. It's 2 over 2n2d cosine theta. And that's the condition when basically m is equal to m is equal to 1, right? Then you will have this 2 pi over here, pi cancel. You have an f, and then 2d cosine theta in the denominator, and c in the numerator. because K is omega over C, or 2 pi F over C. So that gives you the first one, and the spacing is the same. And that's how you get that free spectral range. Okay, the same exact phenomena happens in microwave filters. So in a microwave filter, you can have a filter made like this, transmission line coming in, and then I have a gap, another piece of line, gap, another piece of line. And it's the same thing. You have a wave coming in, most of it is reflected back, but a little bit goes through. Again, most of it is reflected back, a little bit goes through, and over time in steady state, all of it goes through. Because you have one reflection transmission here, reflection transmission here. Then you can cascade them, and that's what these cascaded filters are doing. Right? This is one way of looking at them, but the same phenomena occurs. So that's the time domain version of filtering. Okay, so we covered a lot of topics today, very interesting topics related to dielectric interfaces. So we showed here that you can get perfect transmission, but is there a way you can get perfect reflection? That's an interesting question. Looking at this relationship, it doesn't look like you can do it because you don't have a plus term that can cancel out. And that is indeed the case. You can't get perfect reflection from just 3 interfaces. What you need is a periodic structure. Okay, and those structures are called distributed Bragg reflectors or a Bragg reflector. So when you have many interfaces, periodic interfaces with quarter wavelength spacing, then you can make what is known as a Bragg reflector, and then you can have perfect reflection as well. Okay, so that's not a topic we'll cover here. You can look it up. It's not that complicated, but that's for another video. Okay, so we'll stop here. I'll see you in the next one. Thank you.